Hello good people, I'm going to talk about scientific notation which is used to express very large and very small values. It is a tidy way of dealing with placeholder zeros. I'm going to use the average distance between Earth and Mars, as well as the length of an unassuming bacterium, as examples. These two values, 230 million kilometers and 0.000175 centimeters, are currently written in normal notation. Before I convert the average distance between Earth and Mars into scientific notation, I would like to talk about components of a scientific notation. There are two parts to it. There is the coefficient, which is a decimal that contains all the significant figures. And then there is the magnitude, which gives the value position of the leftmost significant figure. The magnitude is written as a base 10 power. So what does that look like in case of our 230 million kilometers? This distance has two significant figures, the 2 and the 3, and they will be part of my coefficient. However, the coefficient has to be written as a decimal value. This means that we need to place the decimal point after the first significant figure, in this case the 2, and so we will have 2.3. The coefficient must be multiplied by a magnitude, and that magnitude will be written as a base 10 power. So I can already write multiplied by 10. I need the exponent. There are a couple of ways that we could do this. The first one is to think in terms of value positions. The leftmost significant figure in normal notation is in the 100 million position. That is its place value, which means I need to raise 10 to a power that would get me to 100 million. So the question is, to what power do I need to raise 10 to get to 100 million? It is okay if you do not know this. There are ways to determine it. One is being trial and error. The other is to count how many times did the decimal point move. This decimal point in the coefficient, where was it in normal notation? Well, it is an invisible decimal point that was at the end of the value. And so now I'm going to see how many times it has actually moved. Once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times. The decimal point has moved 8 times, and therefore the power of my magnitude is an 8. This means that our value of 230 million, when written in scientific notation, becomes 2.3 multiplied by 10 to the power of 8. Please do not forget the units. They are written at the end of the scientific notation. Let me convert the length of the bacterium into scientific notation as well. This value has 3 significant figures, 1, 7, and 5. These 3 significant figures will make up the coefficient. The decimal point goes after the first digit. So now I have 1.75. The magnitude will be a base 10 power, so I can write multiplied by 10. And now I have to be careful. This value, written in normal notation, is less than 1. Whenever we have that, the power of the magnitude will be negative, so I can already write a minus. From here on, the method is the same. I need to determine the value position of the leftmost significant figure. In this case, this one. It is in the 10,000th position. So now I need to figure out to what power do I need to raise 10 to get to 10,000ths. And once again, I can count how many times did the decimal point move. It moved once, twice, 3 times, 4 times. And so the length of bacterium, when expressed in scientific notation, ends up being 1.75 multiplied by 10 to negative 4 centimeters. Keep in mind that when we have a value that is less than 1, the exponent of its magnitude will be negative. Speaking of values that are less than 1, there is a bit of a shortcut. Rather than counting how many times the decimal point has moved, you can simply count the number of zeros in front of the first significant figure. In this case, we have 4 zeros, therefore the exponent of the magnitude will be -4. I know you are keen to find out more, but let's have a cookie break. That is all for now, and I will see you on the flip side.